Okay. So the trapezoidal approximation is one that tends to show up on every AP exam in free response somewhere. It's one part of one. So let's go ahead and review. What is the area formula for a trapezoid? And I'll show you how they work with curves. Yeah. Area equals 1/2. There's a B1 plus B2 in there, and then also we've got to have height in there. The height. So it's just 1/2 base times height. The way I remember it, it's the same as that of a triangle, but a trapezoid has, let's draw a picture of one. How many bases? 2. A trapezoid has 2 bases, that's all. Otherwise, if you were to take and put dashed lines here and here, slam those together, you have a triangle. So it's just a triangle with 2 bases. That's your trapezoid formula. So what's going to happen here is we'll have some kind of curve. Maybe something like, could be a trapezoid. Like that. But we'll have a curve on a closed interval. We can use trapezoids. Let's draw a couple trapezoids here. One. There's another. That first one is actually reduces down to just a triangle because it has no base 1. But we have 2 trapezoids in that picture. And the trapezoid area formulas, when you add them up, end up being a pretty good approximation for that curve. It's a little bit of an overestimate because this is concave up. But same principle as with LRAM, MRAM, and RRAM is if you add more trapezoid, you get a little more accurate, more and more accurate approximation. So trapezoids work really well. What I've noticed over the years, looking at the free responses, they don't ever ask you to use the trapezoidal rule as it's stated in the textbook. Not to say that they wouldn't, but I'm going to show you the trapezoidal rule as stated in the textbook. It works when you have a consistent delta x. So when delta x is not changing, it works. What I tend to see in terms of them asking you for, and I have a couple examples at the end of the notes, is for what we call trapezoidal sums. They'll give you a table of values, and you're just calculating the areas of individual trapezoids, all with different heights. So you almost have to take and turn your head sideways. Here's my trapezoid. You see the trapezoid, where the height is your delta x. And so if you can think of it that way, I think the trapezoidal rule will make sense. Because here's what happens. The top part of this second trapezoid is the bottom part of the previous one. So what you end up doing is each of the trapezoids, you use their bases twice, as the top of one and the bottom of the next, or bottom of one and top of the next, if you will, as you go from left to right. But the first height and the last height are on the, and that's basically the trapezoidal formula. So let me show that to you. It says this is another option for estimating the value of an integral instead of the RAM method. This is the only other approximation method we'll learn. In BC, we do talk about Simpson's rule. We're not going to do that in here. But it's the trapezoidal rule. It's T equals, big T is for the trapezoidal rule, H over T, so go ahead and write this down, of y0 plus 2y1 plus 2y2 plus, in other words, you're doubling the y values of all those middle ones, okay, which totally makes sense, I think, if you think about those trapezoids, and then leaving the endpoints as just single values. So you got y0 on one end and y sub n on the other end. That's it. So that's the trapezoidal rule, where AB is partitioned into n subintervals, and H equals B minus A over n. So when they say, a lot of times they partition it in such a way that H ends up being a 1 or a 2 or something like that. So it's just B minus A over n. So it's the one endpoint, the right endpoint of the interval minus the left endpoint of the interval divided by however many intervals you have. That's your height. So the height becomes the delta x on the bottom. So that's the trapezoidal rule. put this here to make a picture of it. So you could take any curve, and if you start breaking it up into a bunch of trapezoids here, of equal length, equal delta x, I'll say, but that's what it looks like. And so you end up doubling. Here's y1 right here. There's y1. Here's y naught straight up here. You don't double y naught. That's base 1 of the very first trapezoid. And then over here would be y sub whatever n is. But each of these, y1, y2, y3, y4, I guess this would be y5 in this picture. Each of these needs to be doubled, because it's the bottom of the previous one and the top of the next one. All right. So we'll do one example of using this. There's in the textbook they have somewhere if they give you the function and they tell you to partition it into a certain number of sub-intervals of equal width, then you can roll through it like this. And I'll show you a couple examples of some AP free response parts from the past. Usually it's a part, A, B, or C. It's a part of a free response question is using the trapezoidal rule. Matter of fact, I think I have one up here. I'll give you one tomorrow. Yeah, it does. It's a part D, this one. It says use the trapezoidal rule to find the integral from 1 to 2 of 1 over x dx with n equal to 4. N equal to 4. So here's the setup on this. We're just going from 1 to 2. So each of the partitions has a length of 1/2. Actually less than that, 0.25. 0.25. So if I fill in my x's here, I have to fill in the table. I've got 1, and then 1.25, and then 1.5, 1.75, and then 2.0. So that would be y naught. Write it down here. Y naught, y1, y2, y3, y4. And all of these in the middle will get doubled, according to the trapezoidal rule. So once again, typically you're using the trapezoidal approximation because we don't know the antiderivative. You might want to graph the thing and then just use values. Second calculate value on your calculator to get the values. Probably on this one we could just type in some quick division problems here. So y naught is going to be whatever you get when you plug in 1 to this function. So 1 over 1 is 1. Y sub 4 is going to be whatever you get when you plug in 2 there. 1 over 2 is 0.5, and then we've got everything in between. I need some help with these. So it'd be 1 over 1.25. What decimal do you get for 1 over 1.25? What's that? 0.8, yeah. And then 1 over 1.5 we get 1.67, and 1 over 1.75. What do we get? What is it? So there are, I need to just plug them in here. So you see how we got H here? You can use the formula they give you from the book. They really want you to get away from being formulaic. These are just trapezoids. Think of if I drew a picture of this from 1 to 2. 1 I'm at 1, and 2 I'm at. Just this is the curve right here. And then as I draw my trapezoids, there's one of them right there, and then another one right here. Anyways, the trapezoids have a width of 1/4 or 0.25, and that's the height of each of these trapezoids. So you got to look at it this way. Trapezoid is running up and down. So we've got 1/4 over 2. 1/4 is my height. Y naught is 1 plus 2 times 0.8 plus 2 times 0.67 plus 2 times 0.57 plus 0.5. Add all those up, and that's your trapezoidal approximations. What do we get here? How are you going to do this one? Scramble in there. Does that do next for you?
I can figure out the area of the trapezoid.
Yeah. All right, what do you guys have? And think about if it's an under or over estimate in this case, based on the picture. What's this one going to be? 0.697.
5.
Let's see. Well, that is 1/8 of all that. Yeah. Okay. It's about 0.697 in the nearest thousands. Under or over estimate, based on concavity of this thing. It's going to be a little slight overestimate. Slight overestimate. But that's a trapezoidal rule. Honestly, guys, we're going to be end up using what are called trapezoidal sums. What you're going to end up with is a table of x values that won't be the same width. They typically have you use the trapezoidal approximation when you're given a picture, like you have in the last two pre-responses I've given you. That's a method of calculating the integral. So that's it. Let me show you a couple examples here from AP pre-responses from the past. Everybody got this? All right, here's one of them. As a bug runs along a wire at rates shown in the table below. So you can see it goes from 0 to 2, 2 to 7, 7 to 10. So our delta x is changing constantly. And the velocities or rates at those given instantaneous time, at the instantaneous rates of change is what they are 1 feet per second, 4 feet per second, 3 feet per second, 6 feet per second. If you're going to find the distance the bug travels, it's the integral of this thing. So we're calculating an integral of some function that's not explicit. It's just we're given selected table values. And so we're going to use trapezoidal sums to estimate the distance the bug travels. you could draw a picture. But we know that the height for this first trapezoid is going to be 2. The height for the second one is 5. The height for the third one is 3. Height for this one is 4. And the height for this one is 6. And then we've got our base 1 and our base 2 as we go along, right? Base 1 and base 2. So we've got a whole series of trapezoids. So trapezoidal sums, we have T equals base 1 and base 2. We got base 1 and base 2 of 1, so we got the times the height. So think of a bunch of trapezoids going on here. We've got 1/2 base 1 plus base 2. Base 1 is 1, base 2 is 4, so it's 1 plus 4 times 2 plus 1/2 of, I gotta write 5. 1 plus 4 times 2. And then the next one, we have 1/2 of, this time instead of 1 plus 4, we've got 4 and 3, right? Next 2, so we got 4 plus 3 times the height of 5 plus 1/2. What are the base 1 and base 2 the next two? 3 and 6. Yeah, and that's the 3 plus 6.
Times 3.
Times 3, good. And then plus 1/2. 6 plus 3, yeah. And then 4 plus 1/2. 3 plus 6 again. Times 6. And there you go. So just a bunch of trapezoids. Unfortunately, they're all different heights, but it's okay. Add them all up. You got 5 plus. So you have somebody on this?
My calculator's dead.
Calculator's dead.
That's why we
I charged it.
You could pull that 1/2 out and just, sometimes what I'll do is just pull the 1/2 out, save that for the end, add up the consecutive pieces here, like the 1 and the 4, that's a 5 times 2, 4, so that would be 10 and then 35. You got the 1/2 out here, you got 10 plus 35 plus 27 plus 36 plus 54. Yeah. Yeah, so these end up being the heights of them. All right, what do you guys get?
I'm still slightly down.
Does anybody else get an 81? A 91? Oh, you just got 81?
No, I got it.
Okay, we got an easy one. And so feet, that's how many feet he's traveled. 81 feet he's traveled. Okay. That's a bug on the wire. This next one is taken from, I recognize it. It's from an AP pre-response. The bug on the wire may be from the textbook, I don't know, but it's 81 feet. This is the last one here. This one's interesting. This is the temperature of a container of water was measured at selected times shown in the table below. Find the average temperature of the water during the 20 minutes shown. So if you want to find the average temperature, this takes it a step further. And I've seen this on the AP exam. It's not just the trapezoidal approximation. You've got to remember average value is the integral divided by the length of the interval. So This one you have to divide by 20 at the end. So that's no different. So it would look like this. It's 1 over 20 minus 0. That's your b minus a. The integral of whatever this is, f of t dt. So 1 over 20 minus 0, that integral of f of t dt. And the only way we have to calculate the integral of f of t dt from 0 to 20 is to use some trapezoids there. We got 1, 2, 3, 4 trapezoids to add up. So 1/20th and times, we'll just put the 1/2 out there. That's part of the trapezoid formula, and then we've got a bunch of different heights there. 43 plus 48 times 6. Plus 48 plus 52 times 4. Plus 52 plus 60 times 7. Plus 60 plus 57 times 3. What's that? Yeah, because of the word average and the average temperature, and it's not a linear function. The only way we have to find the average value of nonlinear functions would be to find the integral and then divide by the length of the u. So there it is. We can just do the setup and probably leave it. But average value, I'm going to give you one of these tomorrow for practice as a review. We had a lot of review to do. Okay, so just for homework, you've got page 316, 1, 2, 3, 4, 5, 6 problems here. Just doing some the trapezoidal rule with explicit functions, with tables, kind of a mixture of all. There's the trapezoid. And then you've got about 5 minutes right now. I need you to finish up this functions defined by integrals. I'm going to print a couple for these guys right now. Go for it.
So around the remediation kick in the
Remediation schedule kicks in tomorrow.
Wait, so it's Monday?
Somewhat. It's a little shorter. We're 2 minutes shorter today. It's 9:18.
Wait, you have remediation on Monday?
No, but like,